welcome back to post-lunch session. It is my pleasure to introduce today's this post-lunch session resource person, distinguished resource person, Mr. Balaram Krishnam Raju Indukuri, a highly accomplished professional with over 17 years of experience in VLSI, including 6 years in DFT and 11 years in VLSI research and training. He is currently associated with Tessol Semiconductor Private Limited, Hyderabad, where he leads teams in scan insertion, AT, PG, MBIST, boundary scan, pattern generation and pre-silicon debug on advanced technology nodes such as 14 nanometers, 28, 45, 55 and 90 nanometers. Mr. Raju has extensive hands-on expertise with industry standard EDA tools from Synopsys and Mentor Graphics and has worked on multiple complex projects involving JTAG, IEEE 1149.1, BSDL development, timing simulations, custom scan architectures and memory BIST verification. He has also contributed significantly to academia, having served as coordinator for VLSI design centers, establishing industry academia incubation centers, mentoring UG and PG students and delivering numerous lectures and workshops. A CDAC certified VLSI engineer, he holds an MTech in VLSI design and has published 13 research papers in reputed journals and conferences. We are honored to have such an experienced VLSI and DFT expert with us today. I request Mr. Balaram Krishnam Raju to kindly take over the session.
Scroll yes. Okay. Good afternoon, everyone. I think it will be maybe afternoon always will be a sleepy session, but I don't want to be a sleepy session. I want you to involve in it. Okay. Yeah. So the topic, maybe you can see that design for testability solutions for wireless SoCs, industrial practices. It is not maybe like algorithms or some mathematics we may not be there in it. It is completely implementation perspective of the wireless SoCs. That means whatever the wireless designs or their Kalman filter or some other techniques and everything has to be implemented on a hardware. So while implementing the hardware, what challenges? Especially in the aspect of testing. Testing is a major challenge now. So with that perspective, the session will be more oriented and more focused onto that direction. Okay. So maybe few people may have a background of VLSI, maybe more aligned, maybe knowing the techniques or maybe aligned with that topic. But even who are not having a VLSI background also, they will understand actually what the challenge will be there while testing and chip. It might be the chip, maybe a size is maybe a small size, like ordinary chip size only it will be there, below lesser than that. Ordinary lay chips, lays how many chip, what is the size of this much, but actual our chips will be this much only. It will be much lesser than that. But the challenge is there in a chip is that verifying it. You will be doing manufacturing of the ICs, wireless ICs, or whatever the wireless ICs that is used in automobile or space, or all the wireless ICs, so SOCs, whatever maybe it is being used. But it has to be tested. Without testing, we can't send it to the customer. Okay. So how we will test it? Can you keep a probe into it? IC chip is there. Can you keep a probe like your breadboards? Can you keep a probe into it and check it? How you will verify? How many transistors? Maybe one question I may ask you. So what is the latest processor from Intel? Can you say, anybody? Somebody following current trends? 99, maybe it is more than that now. Intel Altera and Intel Lake recently released a quarter before. It is having around, can you imagine how many transistors it will have? Some blind guess. 10,000? No, it's absolutely not, very small. Can any other guess? 1 billion. It's also small. 5,000 crores transistors. 5,000 crore transistors. So that many transistors are manufactured. How you will test it? All the transistors are correctly manufactured or not? Ultimately, if you want to give some product, suppose whatever ఏ product కొన్నా కొనండి, మార్కెట్లోకి వెళ్ళే ముందు అన్ని టెస్ట్ చేసి ఇస్తారు కదా. So when we are manufacturing in Intel, not only Intel, whatever maybe other ICs, AMD ICs or Qualcomm ICs, whatever the mobiles process, whatever you use it in your phone, they have to be tested before giving to the customer. So then they should ensure that all the 5,000 transistors are manufactured correctly. Okay, general, if the size is very small, we will give a probe and we will take it. But in an IC, how you can probe it? 5,000 transistors, how you can node each and everything, how you can touch it? Is there any way? That challenge will be addressed by this design for testability. So directly if you test it, only outside pins, maybe 500 or 600 pins coming out of the IC, you can test it. Beyond it you can't do any testing. But where is 500 and where is 5,000 transistors? Maybe 500, if an IC is there, 500 pins will be coming out. You can probe it on those 500 pins. But how can I can test it 5,000 transistors inside that was manufactured inside an IC? Any wireless IC or not only wireless IC, it can be any of the IC. Maybe it is much oriented towards the capability, how we will give it to test all these nodes. Our main goal and whatever the topic we are going to discuss is how to feasible to test all the 5,000 transistors inside an IC. What techniques we will use it. Okay. So that is a topic that we are going to discuss today, and actually we will have some demo of one of the designs. I can show you what we are practicing sometime. I can show you some of the design. So some hands-on, maybe I can't give you hands-on, but some demonstration I can provide on that aspect, the practice what we are doing it. Okay. Okay, the main objective of this session is to bring awareness on participants about the DFT domain in wireless SoCs. How DFT is included in a wireless SoCs. Ultimately, your filters and everything, whatever you design, has to be implemented in a hardware. So generally, what do you think about the hardware that will be reflecting for your, suppose morning session we have discussed about Kalman filter. So Kalman filter, when you convert into hardware, what is an equivalent components? What components will use it? Somebody who worked on that implementation aspect of the on wireless. It is nothing but a D flip-flop and a gates. Whatever you do it, everything will be converted into flops, especially only D flip-flop. So maybe digital electronics, maybe you heard about so many flops, JK flip-flop, T flip-flop, D flip-flop, so many flops, SR flip-flop, so many wheels ready. But practically industry, they will use only D flip-flop. Only D. D, inverter, AND gate, OR gate, AOI gates, OAI gates. Only those things will be implementation. Whatever your Kalman filter will be finally converted into RTL form. How an RTL form will be there? Anybody participants have an idea on that? RTL, register transfer logic. Yeah, maybe studied about digital or Verilog, people will know about it. So RTL, how an RTL will be there? Market. Generally RTL means how it will be there. It will be a flop, maybe I can say as a flop, and a COM and a flop, and again a COM and a flop, and a flop. All these things will be connected to a clock. D input, some glue logic design will be there, combination circuit, and it will come. Finally, the inputs. This will be the chip boundary. Suppose if I assume it as a chip, it's not working. This will be the boundary that may have a clock onto this. Okay. So it may have some connections outside also, like this. Whatever it may be, finally it will be there in a transistor. What is there inside this part? All gates. Nothing but inverters, AND gates, AOIs. Only those gates will be there inside it. This will be your D flip-flop. In this form, everything will be converted. Other than this, what will be there inside an IC? Any of the IC, can you imagine? Can you think of it and you can guess it and say, what other components may be there? How it will memorize? How chip will be memorizing? RAM, SRAM, DRAM, memory, and how a chip will be communicating to the external worlds? A to D, analog to digital converters, digital to analog converters, RF front modules or front-end modules will be there. Finally, that output will be converted into analog. Then that analog will be converted into again digital. Finally, these are the components, and few more components. Sensors, temperature sensor or voltage sensors or regulators, power supply regulators, and PLLs, which will supply the clock to the internal circuitry, oscillator sources like crystal oscillators and PLLs. These are all the components will be there. Okay, thank you. Okay, any IC means it's very hard to write in it. ADCs, DACs, memories, sensors, different type of IPs that may be different sensing, any of these sensing ICs will be there, and all the glue logic. What I say is the glue logic. Glue logic is nothing but RTL code, RTL whatever we are discussing now. That is also will be a part of it. So all these components will be there, a part of an IC. Now I want to make sure that IC is perfectly manufactured, means I have to test all the things now. All the things. But today I will discuss a few techniques that will cover this glue logic. That means how we can verify the glue logic. That means make sure that glue logic is manufactured properly. All transistors are manufactured properly. There are a lot of process will happen while manufacturing. What are the different steps we'll have while manufacturing? Any of you can tell? Like lithography, etching. So many steps will happen. In that process, obviously some transistors will not be manufactured properly. We will come to the topic. Yeah, okay. So that failure parts I have to identify it. If it is failed, some transistor is failed, means I should not deliver the chip. I should throw it in a dustbin. Okay. So how to test that? So there is a separate techniques to test the memory. There is a separate techniques to check this glue logic. There is separate techniques are there to do for IPs. Analog separate techniques are there. So there are in DFT, there are so many techniques are there to test each and every part of it. Not a single technique. But most popular one, okay. But most popular one is the scan. That is RTL. This is RTL one. Okay. This has to be verified. So we will try to understand these different techniques. Just I am giving a background what we will be discussing. You will be understanding about DFT, what is DFT in wireless, and understand the DFT design flow. So maybe in a SOC design where a DFT will come, okay, and we will understand different techniques like the scan, ATPG, boundary scan, and MVIST. These are different techniques. MVIST is related to the memory. So scan and ATP is related to the glue logic, RTL, and this boundary scan is related to the all IO pins. On a board, there are so many ICs will be there on a PCB. So how to check the interconnections between IC to IC, that will be done by this boundary scan. So all these techniques we will try to understand. Okay, first we will see about the overview of wireless SOCs. Okay, maybe this part, maybe you may be familiar with that. Basic building blocks generally will include RF front end, baseband process, memory and power management. Why power management is so important is that all modules will not work on the same power. One module may work at 0.5 volts, other module will work at 1.1 volts, some other module may require 2 volts also. Some modules may work only with 500 or 1.1 volt also, some modules will work. Like that, different subsystems will require different power requirements. And to manage the power delivery to each and every subsystem, we use power management and so many connectivity interfaces. So there are so many connectivity interfaces like Wi-Fi, Bluetooth, all are wireless connectivity interfaces. All those things are the building blocks of any of your wireless SOCs. Okay, so maybe if we can replicate that in a diagram, you can see here RF switches, RF receiver, trans receiver, some multipliers and analog receivers, analog transmitters. 1/2 is nothing but a dividers. These are the voltage controlled oscillators and PLLs. What we crystal, that means oscillator sources, and biasing circuits are there, power management units will be there, and we will also have accelerators. Nowadays this role has been increased a lot, accelerator, because of the chips currently they are generated, they have to have a capability of AI, artificial intelligence. To handle that AI, we need more and more accelerators. Hardware requirement for the accelerator is very huge. Other than that, we also have so many interfaces like SPI, like GPIO, I2C, so many protocols are there. CAN, automobile if you are using, they will be using a CAN. So all the SRAMs and the digital baseband, these are the different components you will have it. Okay. So I don't think that there is no need to explain all these things. Baseband processors that will deals about Wi-Fi, Bluetooth and 5G application processor that is generally that ARM Cortex will be used for application processors. Memory subsystems will be SRAMs or DDR RAMs. So maybe all these components you will have it in the front end. Then connectivity interfaces like I2C, UARTs, SPI, PCI, PCI Express, PCIe means Express, okay, GPIOs and power management units, security engines, especially cryptography, decryption and encryption of any data is needed. So those type of engines also will be there inside any of the SOC, any wireless SOC. Especially this security engine is so complex, it's becoming nowadays because of hacking of the components. It will happen mainly through the security engine only. If security engine is not proper, you can hack the PC or a hardware. Okay, multiple protocols interfaces like Wi-Fi, Bluetooth, Zigbee and all those things. Okay, so I am not going more into it because I want my concentration is more on the testing part. Maybe if you see this image, maybe some idea like SRAM is there. For SRAM, MBIST is the technique that is used for it. So there is a PLL. For PLL, there is a SERDES will be there, serial parallel interfaces will be there, and core logic, that is RTL code. For that scan, compressor and scan, that is a technique is used for this. DDR RAM, for this also MBIST will be used. Like the different techniques will be used for different components inside an SOC. Yeah, basically if you see SOC design flow, first it starts with the specifications. That means what capability you want and make IC. Whether it want a Bluetooth interface, whether it wants wireless. Wireless means how much range, how much strength you want it, how much noise suppression you want it, and all those components has to be given as an input. That's called the specifications. For that we have to design. We have to design an architecture. That means architecture means we have to come up with one block diagrams. That block diagrams internal content you have to work out, and internal content also has to be designed, and how the blocks, individual blocks will be there, partition of all the blocks, and what is the architecture inside the block, what is the hardware you are expecting. Before generating an hardware, you should have how the functionality should be there. So all those information has to be provided in the architecture design. Architect designs will be the topmost jobs that generally they will have it at CEO level. So at that time they will be doing architecture designing. Okay. Then it comes to the RTL designing, where that specifications will be converted into hardware descriptive languages. Maybe you can use Verilog or you can use VHDL, whatever maybe language you can use it, but RTL form will have to be converted. RTL form is nothing but again register transfer logic. So once it is converted, then RTL has to be verified. So many techniques are there to verify the functionality. That verification and what we are saying, the testing is completely different. We will come to a discussion to that point. Okay. So the verification what we do will be different than the whatever the verification, RTL verification it is done. So what you will do in RTL verification, the functionality of the RTL code but not the hardware. There is no hardware. You are not verifying the hardware there. Functionality of that we are verifying. Okay, but our intention is that manufacturer testing. That means after manufacturing, we have to test it. That perspective will be covered by the DFT, but this verification will ensure that the circuit is correct, the design is correct. Design is correct. So like house plan will be different, but after construction it can be different. Okay, first of all the plan is correct or not, we have to define. No, that will be defined by your RTL verification, not the structure of the design. Structure is not verified by it. Structure will be verified only after construction only. Structural test has to be done if you convert the same problem into civil engineering problem. Okay, if you frame certain beams for a house, how much strength is that beam? On paper different will be there, but after construction what is the strength? So that the DFT will do it. Before designing on paper what we will design it, that will be done by RTL verification. Okay, then the synthesis, that means that will convert into hardware, not a directly hardware, but what are the gates and what are the transistors, what are the flops we need it, and all those stuff which will be converted after synthesis. There the question of DFT will come. Most of the role will be happening after synthesis. Okay, then floor planning, where the layout will be formed. Maybe people may be drawing the layout designing. How many of are exposed to that, I am not aware of that. But we will draw a layouts of the transistors. So that layout conversion has to be happen. For that floor planning is needed, and placement of each and every subsystem we should be defined, and connectivity between that, and a clock tree synthesis is the most important part. So I am not going more detailedly onto this because I want to cover the actual DFT techniques. Okay, so just on a broad view, if you want to give, CTS means clock tree synthesis. Why clock is so importantly placed is that each and every transistor has to be provided with the clock. That too, clock should go to each and every flop. Suppose in my design 10 crores flops are there. All 10 crores flops should get the same clock at the same time. By the paper it is good, but when you keep it on hardware, the wire delay will be there. Because of the wire delay, all the clocks will not get the clock signal at the same time. There will be some delay. That delay has to be addressed. That has to be also taken care in CTS. Then routing means what are the ways, like you are building, how the road network is built, 80 feet road, 100 feet road, and decide routing has to be decided. So that task has to be done. And then fabrication. After fabrication, it has to go to the, after fabrication it comes like a wafer. On a wafer dice will be there. That has to be packaged. After packaging and testing, then a real chip will be ready. Most of the industries now in India, activities are going on, packaging and testing. So many industries are coming on packaging and testing. Okay, so then the final chip will be ready. So this is the general flow. So in this, DFT will come not only here, there are other places also. We'll come to the next slide, that one. Okay, after a while we'll come into that point. So generally manufacture testing, that what is our goal is that after manufacturing we have to test it. So how the defects will be there? So some shots will be there like this because of tiny particles. They will be dressing out so that no dust particle will enter into the fabrication facility. So still they will have some particles that may cause a shorting. If it is rejected because of failing, they have to throw out, and only passing ones has to be passed out. That means the yield. Generally, suppose in practice what happen is that if I manufacture 100 chips, out of that I will throw 30 chips into a dustbin. Only 70 chips come out. Okay, after that 70 chips also has to go to all the stress. They will be keeping in a funnel and they will be providing the heat wave to it, and then also they will test it. That also has to be passed. So all mechanical testing will be happen, electrical thermal testing will happen, and all those type of all the stress testing also will be happen on this each and every IC. So finally that goes through will be very little. Nowadays in current technology, around 1 nanometer, 2 nanometer chips we are getting it. The yield is very low. If you manufacture 100 chips, 10 or 20 chips are coming out. 80 they are throwing out. So that is the cost, it is becoming more. So that's the reason they are concentrating more on the quantum computings. So that is emerging. Maybe the next technology may overlook this type of CMOS or FinFET. Right now, what is the transistor models you are using it? Are you having any idea? Transistors are using BJTs? FET. FinFET. CNT, that is also over actually. Gate around, gate all around, have you heard about it? GAL FETs, gate all around FETs, that's the technology going on at 1 nanometer, 2 nanometers. That means around the gate, complete round will be the, around the silicon, complete round will be the gate, not only on the surface. Gate around, that technology is going on, but we are not going to discuss on that. But that much advantage, advanced stage, the designing has went into it. Okay, that's not our topic now, so we will not go into it. Okay, then. So these are the different type of defects that may happen, like glass damages may happen, and some patch has been gone here, and some particle has been shorted here, some large portion of that has been here, line breaking has happened, here mouse bite we will say it, that means a small portion of the metal will be cut. Like on your roads, some temple or maybe there, they will cut it, and beside that they will be laying the road, no, it is like cut. That we will call it as a mouse cut, that type of. It's another one is a bridging type. That means two metals will be shorted. Yeah. There will be 4 possible outcomes when you do a testing. So I want to, this is much important, that's why I want to keep this one. So good chip, good IC means pass test. Okay, there are defective ICs and good ICs. There are 2 categories here, good ICs and defective ICs. Okay. If we test, if all the tests it passes, then it comes under the true pass. Okay. So failed test, if it is failed, IC, if it is failed, then also it is being categorized as a good IC. It is escaped, actually it is escaped. Then we will call it as a yield loss. That means it is failed the test, no? Actually it is failed the test. We are expecting it is a good one, but it is failed it, so the yield is lost. That means out of 100 chips, some chips will be active and some will be failing. So those we will call it as a yield loss. That means, okay, at least it is identified it is failed. If it is identified it is passed, that means it is passed and it is a good chip, then there is no issue, it is just passing. The most problematic is one is a defective IC. In a defective IC, if it is passed the test, one IC is defective, but it is passed the test, that means escaped the test. That we will call it as a test escape. This is more dangerous. This is more dangerous. If it is good, it is passed, no problem. If it is bad, we throw out into the dustbin, that is also yield loss, that is also no problem. But if it is a bad chip, it is passed the test. That is called test escape. That is more dangerous. Okay. Other one is a true reject. Chip is defect, test also failed. So that is right decision only. These two are the right decisions. These two are the failure ones. Even this also will not cause a major thing. Good IC can also be thrown out. By mistake it is failed. It's a good IC only. Reading may be wrong. still we will throw it off as a doubt. Why to have a doubt? But if really defect is there, if it is escaping it, test escape will happen. These things will cost a lot. We don't want these things, test escape should be happen. Our goal is to reduce the test escape. Few technologies are there here, yield, that is nothing but simple number of good chips by number of total chips. మొత్తం total chips ఎన్ని good chips ఉన్నాయి, that's it, simple equation. Fault coverage, number of detected faults by number of total faults. Maybe you will come across what is a fault, what is the meaning of a fault. Fault, just I will define it as a fault is a mathematical representation of one defect. Some defect is there in a design. Two lines are shorted. Suppose two lines are shorted. How mathematically we will say it? So something happening means everything mathematically we have to convert, no? So then we will call it as a struck at one. Struck at one means two lines are shorted. It is been or metal is connected to a supply, power supply. Then whole metal will be always get a one only, no? So never it will get a zero value onto the wire. So struck at one, that is a mathematical representation of the fault. Like that each and every wire they will test for struck at 0 and as well as struck at 1. Okay, so we will come across it, though that is the numbers that defines the yield, fault coverage. So finally the thing what is calculated is the defect level, that is 1 minus yield to the power of 1 minus fault coverage power of, okay. So this is a small equation, but generally it will be very less, should be less than 200 defect parts per million. Out of 1 million, how many parts are defect? That will say is the quality of the chip lot. Some chips of 1 lakh chips are manufactured. Out of that 1 lakh chips, what is the DPM? Okay, they will calculate. Based on that, they will be checking the quality. Like the quality check in a college. How many research papers you do it, how many citations are there, what type of paper publication you have done, what type of college is that. They will metrics they will form, no? Like that also, what is the quality of the chip? Lot, certain lot of the chip, what is the quality of that? That will be measured by this defect level. Okay, these are the few terminologies, that's why yeah, we're coming to the topic why testing is important. Guaranteed IC quality. Obviously IC quality you want it good, no? So suppose you purchase a mobile, if it is not functioning properly, it is so annoying to us. So if it is not working on your side, on our mobiles, it is okay, we will go to the shop and we will repair it. Suppose IC is manufactured, it is kept in a space mission. If it is failed, what will happen? Can you replace it? No. The whole mission of crores of rupees will be lost. Or if you are traveling, brake monitoring or so many advanced techniques are there in a car, like a brake management system or so many techniques. If some chip is failed and that prediction is not happened properly, what will happen? Life is gone. There is no replacement for it. So that is the reason chip IC quality of the IC that is being delivered to the customer has to be verified at most care. 99% we should ensure that it will work. That means all the transistors, as initially what I told you, like 5,000 transistors are there, each and every transistor is manufactured correctly or not. I have to read the values from it and I have to know it. Only then I can say that it is a good chip. Okay, that has to be done for not only one chip. 1 lakh chips are manufactured. All 1 lakh chip also has to be do that same process. ఒక చిప్తో అయిపోదు ఇది. 1 lakh chips చేస్తే ప్రతి చిప్ కూడా ప్రతి ట్రాన్సిస్టర్ కూడా చెక్ చేయాల్సిందే. Otherwise they will not release into the market. They will throw it off. Okay, so that much of importance is that. Reduce test escapes. Just now we discussed about test escape. That is more costly actually. That means a defect is there, still it is passing the test. That should not happen. Okay, that is very dangerous. These test escapes only will come to the customer as a malfunctioning ICs or malfunctioning phones. Okay, so that is the cause of that. Not only functionality correctly, but also reliability of an IC is important. It's not only functionality. Just the functionality is good of an IC is not sufficient. Reliability, how good it works. Even for 10 years it works good, 15 years also it is good, working good means it is very nice. But like mobile phones, 2 or 3 years we are changing it. But few applications we can't change it. So space applications, if you send it, some IC is manufactured for space application, it should work for 15 years or 10 years or something is the lifespan of that. During that period it should not fail. So that is very important actually. Diagnosing defect ICs to improve yield. Why this is needed, diagnosis? Chip is failed. What is the need of doing diagnosis again? Next chip should not fail, no? What caused this chip fail? Like post-mortem. Some person has been murdered. What is the reason? How he has been murdered? Because of what he has murdered? How much time he is alive and after that he failed? And what organs are damaged? How it is being damaged? How the cut is there? So all these analysis post-mortem they will be doing. We will be watching TV, so we can say so much of thing post-mortem. The same thing, failed chips also has to be diagnosed. So all the failed chips are failing at one case only or different cases. Is there any linearity in the behavior or any similarities in the behavior? That has to be verified. So that analysis has to be done also. Diagnosing also has to be done. So next is reduce test cost. Another one is that reduce test cost. Testing, how can we can spend more on testing? If you spend more on testing, the product cost will be more. Do you know if you are purchasing a IC that is costing around 2,000 rupees, how much rupees they will be spending on testing that IC? It is 30% of the whole cost will be spent on, if it is spent for, if I make it as a simple as 1 rupee, out of that 1 rupee, 30 paisa will be spent on testing it only. 70% is only manufacturing, 30% is the testing aspect. So that much of more it's going up. It's not like this 10 years back. 10 years back they used to spend 2% to 3% of the budget they used to spend on their testing. But now they have to spend 30% of that on testing. Because why? Number of transistors are increased, functionalities are increased, so many features on your mobile phone IC. Maybe you are doing it just like that we are doing it. We are taking a photos, we are editing it and different enhancements we are doing it. So all those enhancements, it may be slight, like your mouse only it will be going loud and your finger will be going like this and you will do it. But background, so many DSP algorithms will be running. All those things will be there on the chip. Along with that, it should be handling the Wi-Fi. Along with that, it should be handling the Bluetooth. Along with that, they should be playing so many background data has to be stored and sorted out. So much of background apps has to be installed. That activities, so many software activity will be there, APKs that has to be processed on background. So many sensors has to be running, temperature sensor has to be running parallelly on background. So all those data has to be running along with this task. So multiple tasking has to be done. Like continuously, all the days, continuously days on days it should be working. Okay, so maybe it should be fix defective chips if possible. Can you fix a chip? Suppose some damage has happened in a chip, inside a chip. Can you fix it? We can't, but still we can do it. That is possible in the case of memories. Repairable memories. We are having a concept like repairable memories where few bits can be corrected. Extra rows and columns will be provided like a spare. Suppose we are having a bike, no, so not a bike is possible, for a car. Extra one wheel, spare wheel will be provided. Like that for memories, they will have an extra few rows and few columns. So certain, suppose one of the cell is being failed, that row and that column will be replaced by one of the row and column on extra spare ones. Like that slight correction can be happen, not more than, not 1%, less than 1% only we can correct it. Small errors we can't throw it IC, you know. Small 1 or 2 things are there, we can correct it. But maybe in future new techniques may come that like the self-healing, like our body how it will be healing on our own. like that they are working on the self-healing. Identify, they have to test it, identify it, it should be self-heal without doing anything. That's activity is also going on. Maybe we may see in future about self-healing. It's a very interesting actually.
Sir, what conditions may cause single cell damage in memory?
Single cell damage in memory, fabrication. Simply saying fabrication. How they are manufacturing, because it is a lithography and a high concentrated ultrasonic waves that has to be done on a chip. Some particle may damage it, or influence of the side cells also will damage it sometime. So if some of the cells beside that cell has a more inclined as a, instead of 1.2 volts, it may be there 1.5 volts on that. It will have an implication on a side cell also. It may not show as a defect at the time, but beside that cell may damage.
Generally, we used to say the memories in bytes, gigabytes, megabytes.
Yes, yes.
So extra rows and columns, how can they contribute the repair of the single cell damage?
Yeah, even it is a gigabytes memory, few bits can be corrected, no?
That means we generally use 8 columns and multiple rows.
Yes, multiple rows, correct. So on a hardware itself, extra spare rows will be provided. Extra memory will be provided. Only that is used in the case of failure only. General case they will not use it. It's like a spare, they will leave it. If the chip is failing, then they will try to repair it and deliver to the customer. On the hardware only, if fuses will be there, so they will program the fuses and then they will set that that row and column to replacement of the failed one. The fuse will happen only once. Again and again that you can't use it. Only one time fusing will be happen. Okay, that technique they will use it. Okay, go to the next slide. Yeah, if IC is failing at this stage, cost will be very less. If it is failed at the warranty period, cost will be very high. So it is only half a dollar. But if it is in a warranty period, product came with you and you are using the product, at that time they want to replace, means $500 it may cost them. So that's very costly. Once it comes to the customer, if it is failing, means it is very costly. When it is at the fabrication, then if it is failing, they identify it, while testing means it is very less cost. It's just they will replace the chip. Material is nothing. Material is nothing. Silicon, it is nothing but a refined form of sand. Material costs nothing, but designing cost is the more here. So similar thing on this, at the chip level 1x cost, at the board level it will be 10x cost, it will be becoming 100x at the system level. In servers they are using it. So again some chip is failed, means replacing is very costly. When at the manufacturer only, whenever they are testing it, it is failed, means it will be less cost. Yeah. Okay, this is the verification. Just a few slides back we discussed about what is verification and what is testing. That I want to give more focus on that. Design verification, another one is testing. So design verification means it will enhance, it will make sure that your functionality is correct. Functionality ante, suppose some gate is there. So if you give 1, 1, output should be 1. If you give 0, 1, output to be 0. That functionality only it will checks. If functionally that is whatever you write in is correct. But whenever the chip is manufactured, it is failing. Do you mean that functionality whatever you have done is wrong? No. Because of one of the input manufacturer inside the gate, some manufacturing defect has happened. Because of that, behavior has been changed. Okay. So that we can't identify with the design verification, because design verification means only some test cases only you will give it. Not all the test cases will be given. So whatever the test case you will give it, that may trigger the SAN gate or not, we don't know. It is buried very deep into the IC. We can't say that your test case, whatever you are giving to the design, will trigger that gate and that input, that particular input. We can't say. Okay, so it is not effective to do so. Next. Okay, so why we need, so one specifications is there, Then we will go to the design. So this specification and design both are same or not, we will use a verification. Design verification. What most of the people use, model sim, very popular one. That is design verification. What is testing means, after design is done, silicon came, that means manufacture is completed. So at that time, the design and silicon both are same or not, that is called testing. Simply say. Okay, that is verification is different, testing is different. Excellent. So key differences here, verify correctness of the design here, and explicit testing is nothing but verify correctness of the manufacturing hardware. After manufacturing, hardware is manufactured correct or not. That will be verified by that. Okay, performed by simulation, hardware emulations, but explicit testing is performed by test pattern generations. We will generate a different type of patterns. Those patterns will target a specific gate, specific metal, specific wire, they will be targeting it. And they will extract the information on output. So very specific one will be there generated, that is using the test patterns. Not like simulations, whatever you do it in model sim. Performed once prior to the manufacturing. Only once it will be performed. But what is explicit testing has to be done on each and every chip, whatever you make it. So whatever from the factory, 1 crore chips are coming out. Each and every chip of that has to be gone through the testing. But verification, only first chip we will be verifying it. But all the chips has to be done by the explicit testing. So testing is so important when the products are more. So responsible for quality of the design, that is responsible for the quality of the device. This will give the good design is correct or not. That will give the device is correct or not. House plan చేస్తారనుకోండి, ప్లాన్ బాగుందా లేదా చెప్పేది ఇది, హౌస్ కన్స్ట్రక్షన్ అయిందా, కన్స్ట్రక్షన్ బాగుందా లేదా చెప్పేది అది. That is the only difference. After construction, how is the quality? On paper it may be good, on brochure it will be good, the design will be good, but after manufacturing it should be also be good in the same. But if wall is having a cracks or it is having a very weak conditions, that we can't say it as a reliable one. That we will be getting with explicit testing. Next, manufacturing testing. That is nothing but explicit testing is nothing but a manufacturer testing, where what we will do in that manufacturer testing is that verify whether the design of manufactured correctly or not. Simply it verifies the whatever the IC is manufactured, that is perfectly manufactured or not. How we will be knowing? So how we will be knowing? Test verifies the internal nodes are toggled. So there will be so many wires will be there internal to IC. Everybody accepts no layout design, so many wires will be having. Each and every wire, they will keep a one on this. Each and every wire, not saying few wires. Each and every wire, they will keep one on this, internal to it, and they will bring that one back onto the output. That whether we can keep a one on this and bring that one onto the output. Okay, both will be verified. Like that, how we have to do for all, suppose we are having 5,000 transistors, 5,000 crore transistors. All 5,000 crore transistors, we have to keep a one and again read the one outside. So 5,000 times, 5,000 crore times, again keep a zero, again read a zero onto the outside. That also has to be verified. That is called a structured faults. Other type of verification also will be there. That is, if we give a zero, then if you change it to 1, so within a time it is changing from 0 to 1, or sometimes it may not change, it may take a long time to change to 1. So how fastly it is changing from 0 to 1 also has to be verified for each and every wire, for each and every chip that is manufactured. Both has to go done. Okay, in the same way 1 to 0. So whether it is coming immediately or it is coming after long time. Within time it is working or not. So 0 to 1 transition also verified, 1 to 0 transition also has to be verified, whether the wire is not stuck to 0 Can we toggle the value onto the wire? That also has to be verified. For each and every wire, that should be done in each and every wire, and also each and every chip also. So 1 lakh chips they are manufacturing means all 1 lakh chips has to go through that test. That's not the case with test verification, the design verification. Okay, that is a statement, second one it is saying about it. Yeah, the third one is ability to set internal loads, controllable and observable. Suppose, okay, that I will come up with the diagram. Okay, generally test process is this one. We will give the patterns to it. This is your IC. It comes out, output response will come. That response with ideal response. What is the response it wanted? If it is matches, it compares, it is good, it will passes. AT is nothing but automated test equipment. Tester, on the tester they will keep it and they will verify. It is a very costly one. Maybe generally it will be 1000 crores will be there for only one test equipment. For only one test equipment. Maybe one image is there, maybe next slide. Yeah, maybe some equipment like this will be there. That can test only 2 to 4 ICs that can test at a time. Or if it is a memories that can test up to 32 to 64. This is very costly. This is very costly. We have to pay the test cost to use this equipment. This facility is very huge. So very few companies are having this facility. In India we are not having mass one. We are having few ones that is very cheaper ones with a very less capability. But mass commercial ones we are not having in India. Samsung is having very good in it. South Korea, whatever the chips, whatever design, whatever the DFT we do it, we generally work on the from South Korea. South Korea we will be connecting a server and there we will execute, there actually things will happen and we will see the reports here. But never we will do it on our head. But we will touch it, we will not be physically at the tester, but we will access the tester remotely. Okay. So that's very costly, tester is very costly. That is the reason test is very cost. Then this is one, it is actually the physical defect. Then it is a fault. That mathematical representation is nothing but a fault. Because of what will happen? Error. Because of error, failure will happen. Behaviorally it is a failure, physically it is a defect. Logically, mathematically it is a failure. Mathematically it is a fault. Physically it is a defect. But signal wise it is called an error. But functionally what you say that it is failure. Okay. That's just a replication of this abstract levels. Okay. Then why fault models? Just now I told fault models is nothing but how you will represent the defect. Fault modeling is nothing but how you will represent the defect. So here what I can say is that how many possible defects in a circuit, why too many number of faults can be easily calculated in a circuit. So here what is the fault model means, each and every wire, if it is struck to 0, we will call it as struck at 1. So maybe next slide it is there, it will come on to that. Yeah, can you go to the next slide, it will be easy to that. Yeah. Suppose simple AND gate is there. You can see a power supply is connected to the one of the input of your AND gate there, A input. That means that can I keep a 0 on this A input? Never. Because always it will become as a 1. Now we can't make it as a 0. So that we will call it as a struck at 1. That means that metal has been always struck to 1. That we will call it a struck at 1. That is a one fault model. Struck at model. That will call it a struck at model we will call it. On that struck at model, two types are there, struck at 1 and struck at 0. Another one may be grounded, OR gate. It is grounded. Always it will be grounded. No other logic will come on that. Okay. So another different types will be there. Another one are transition faults. This is a struck at faults. Those two are struck at faults. Another one is the transition faults. Transition faults means just I explained here. So 0 to 1 transition. How good it is transferring. That means it should start here. It should be coming by this time. But if it is not coming by this time, it is coming lately means that slow to rise problem is there. Okay, so slow to fall means it is expected to fall like this, but actually it is coming like this. It is expected at least by this time it is expected the value, but it is coming lately, it is going to 0. That is slow to fall. Than expected, it is becoming more delay. That will calculate the delay part of that also. The gate is correctly working or not, whether it is giving correct value or not, it is correctly within time it is giving or not. Whether you went to the railway station to catch the train is not important. Within a time you went it or not, it is important. Otherwise, logic will not work. You can't travel. Even if you go to the railway station, you can't travel if train is gone. Okay? So this one is also important. Other one is the bridging faults. Bridging faults means one wire will be there. Because of two metals are very close, the influence of that metal will have an impact on the side one. ఒక మెటల్ చాలా స్ట్రాంగ్ వోల్టేజ్ ఉందనుకోండి, పక్క మెటల్కి ఇంపాక్ట్ ఉంటుంది. మేబీ యూమే పక్కనోడు చదువుకుంటే ఇంకొకటి చదువుతాడంటాం, పక్కనోడు చెడిపోతే పక్కనోడు కూడా చెడిపోతాడంటాం, ఇన్ఫ్లుయెన్స్ వల్ల చెడిపోతుంటారు. అలా కూడా కొన్ని ఫాల్ట్స్ అక్కర్ అవుతాయి. దిస్ టైప్ ఆఫ్ ఫాల్ట్స్ విల్ హ్యాపెన్ ఇన్ ద మెమరీస్. So, madam, you are asking about fault, how it will happen in memory. No, this is one of the reasons also. Bridging faults. Major things will happen in bridging faults. In circuit also, few circuits will be very close. If I draw two metals very close to it while doing routing, the step that is been explained before, that may also cause the bridging faults. Okay. So to avoid it, next time when they design it, they can't correct it. Only they can detect it. Okay, next time, if it is a memory means, okay, somewhat we can do it, but other ones we can't do. So, yeah, there are so many faults are there in memory. I can say 20 to 30 different fault models are there in memory. Okay, so it's a lag of time because it's only a 2-hour session. I can't say all the different models. Okay, we will go fast. Okay, next one. So what's the time now? Time and then. 3:10. So do you want to have a break? We'll see what is the next slide. Okay, well, another one slide will complete and then the topic will be forward. Okay, test process. What will happen in a test process? The test process will involve 4 steps here. One step is that what fault to test it. First of all, you have to decide stuck at 0 you want to test it, or stuck at 1 you want to do it test it, or slow to rise, or slow to fall, or a bridging fault. Which one you want to test it? First you have to, for every test there will be a separate pattern. One pattern cannot solve all the fault models. Each and every fault model, one tested pattern has to be generated. So we have to define which fault you want to do it. Next is how to test pattern obtained. Test pattern generation. You have to generate the pattern. Generate the pattern means you have to create some signal onto the input to trigger the 0 or a 1 on that node. Okay, that is the next step. Third step is that how fault simulation. How many nodes are there in IC? How many nodes are tested? Accounting. So suppose 5 crores transistors are there. If I tested only 2000 crore transistors, then I will have only 2000 out of that will be 40% of that. So it may have a coverage of only 40%. So that accounting will be done by the fault simulation. Finally, what has to be done? Test vector applied to the tester. Whatever the test patterns that you generated here, no, that has to be given to the tester. AT emission, what I am showing, no, that will be residing somewhere, some other country. But this test patterns we have to deliver to them. They will test and they will come up with the result to us. On a physical hardware, they have to apply this test pattern. Okay. Before that, these are the 4 steps generally we will follow while doing a testing. Okay. In the next session, what we will be discussing is that after the break, okay, different DFT overview and the flows we will see, And at least maybe time may not be sufficient to me discuss about the memory and boundary scan. At least scan, design, we will fastly look into it. At least one demo we will see into it. Okay? Okay? Okay, then we'll have a break of 5 minutes and then we'll come back.
Participants, there will be a small break, 10 minutes break. At 3:30 all of you are assembled.
So start just now. Okay. Presentation. Okay. Okay. We will see about DFT overview, maybe, and flow of that, and then we will see about the scan techniques. Okay. So next topic is very important is controllability and observability. Actually, DFT is nothing but equivalent to controllability plus observability. So what does this say? Suppose some circuit is there like this. Can I control? Suppose G1 is there, output is there, some F node is there. Can I control a 1 onto that? Controlling a 1, can I keep a 1 on the F, node F? How I can keep? By making A and B and C is equal to 1, 1, 1, I can make F is equal to 1. So suppose I want to test stuck at 0 on node F. Stuck at 0 means what? I should prove that it is not stuck to 0. That is the meaning of stuck at 0. So to prove that it is not stuck to 0 means what I have to do?
All should be 1.
I have to keep a 1 on that. అంతే కదా, మీరు దొంగ కాదు అంటే దొంగ అవును అని ప్రూవ్ చేసుకోవాలి, దొంగ అవును అంటే కాదని ప్రూవ్ చేసుకోవాలి. అదే కదా టెస్ట్. ఇక్కడ ఏంటంటే ఫాల్ట్ ఉంది అని చెప్తున్నాం, స్ట్రక్ ఎట్ 0 కాదు అని ప్రూవ్ చేయాలి. కాదు అని ప్రూవ్ చేయాలంటే దాన్ని 1 పెట్టాలి, రివర్స్ వాల్యూ పెట్టాలి. సో ఐ వాంట్ టు టెస్ట్ స్ట్రక్ ఎట్ 0 ఆన్ దిస్ F. For that first one what I have to do is that I have to keep a 1 onto that. Is it possible to keep a 1 by these inputs? It's possible. That is called controllability. So that one has to be propagated to the output. Chip output has to be propagated. Right now imagine that chip output is nothing but a Y and Z. So observability, the F value whatever you forced it, that can be observable here or not. So can you observe it? Can the OR gate should transmit the 1 here to the output, means what should be the other value of OR gate? It can be anything, X. It can be X, any value. So A and B can be any value so that we can transmit it. But is node F controllable and observable? Yes. Answer is that yes, we can control and observe the node A. Like that each and every node. This is also one node. This is also one node. This is also one node. Even fan out is there, 2 wires like this. Here also one node, one node. This is one node. For each and every node, we have to do stuck at 0 and stuck at 1. Like that, how many patterns will be there for me? For a small circuit like this. Can you imagine how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 32, 14 metals. So 14 into 2, 28. For small circuit like this. For big circuits, it's a challenging there. So finally, controllability and observability is nothing but whether you can control a particular node to whatever the value you want it or not. The same value, can you observe the same thing on the output of the IC? That means on the primary output of an IC. So can you control a certain value on a particular node from the primary input of an IC? Here is a primary input of IC. That means big IC is there, only 500 pins will be there. So one transistor is there in between the IC somewhere. I should be able to set the one by giving some input pattern onto the input. Input lo oka sequence ivvali. దానివల్ల లోపల ఉన్న ట్రాన్సిస్టర్కి ఐ షుడ్ బి ఏబుల్ టు సెట్ 1. దాట్ ఈస్ కాల్డ్ కంట్రోలబిలిటీ. సెట్ చేస్తే సరిపోదు, మళ్ళీ దాన్ని అబ్జర్వ్ కూడా చేయగలగాలి అవుట్పుట్లో. ఈ 2 పాసిబుల్ అయ్యిందంటే ఆ నోడ్ ఒకటి చెక్ చేయగలను నేను. Like that, how many nodes I have to check it means if 5,000 crores are 5,000 crores transistors are there means that many nodes also have to do it. Okay. So that is nothing but controllability and observability, basic definition of that. Okay. So this is the original, previously traditional way the design used to be there, and after the design is happening they used to test it. But now what is happening is that for design, along with the design, we are also having a DFT into it. Design for testability. That means it is not testing. We are adding a new hardware such that it will bring the capability to set a 1 or a 0 on a particular node. So maybe in the previous example you can directly set it, but if it is very deep into the IC, all the inputs are not directly connected to the primary input of an IC. Is it possible to set it? Somewhere deep into IC it is there. I want to set it by inputs. Is it possible? No. We have to add some hardware to make it set. That hardware is nothing but we will call it as a DFT. Along with the design, if you keep DFT, only it is possible to test it. Test will be done by other team. But to enable the testing, we will be adding DFT hardware. This DFT hardware, customer will not use it. So end user, if you are purchasing a IC, you will not use the DFT hardware. You will be using only the design. But why you are keeping DFT is that we are keeping almost 30% of the extra hardware we are keeping. మీ ఫోన్లో ఉన్న దాంట్లో ఐసీలో మీ ఫోన్లో యూస్ చేసే ఐసీలో యాక్చువల్గా మీరు ఉపయోగపడేది 70%, మిగిలిన 30% బర్రీడ్ అవుట్. వీ కాంట్ యూజ్ ఇట్. ఓన్లీ డ్యూరింగ్ టెస్టింగ్ ఓన్లీ ఇట్ విల్ బి యూజ్. ఓన్లీ వన్ టైమ్ ఇట్ ఈస్ యూజ్డ్. So to define the chip is passing or failing, only for that it is used. After that we will not use that 30%. So literally you are purchasing only 70%, you are paying for 100% even for testing. Okay. So it is buried out. This DFT logic we can't read it after packaging has happened. Before packaging only we can read it. Flexibility of that will be grounded for security reasons. People what they are doing is that with this DFT they are hacking. They are hacking the chips using the DFT resources. They are trying to understand, replicate the internal content of the chip using a DFT hardware. So they will be burying up inside it once the chip is manufactured. Okay, next. Why DFT? Main DFT is used to reduce ATPG effort. That means just now in an example what we have seen, for a small circuit we have seen about 28 different checks we have to do it. So that's very huge number. So that number of test cases should be as small as possible. This DFT can do it. The test cases it can reduce it. Okay, improve test quality. Obviously the reliability of the chip will be improved. Reduce test cost. Number of patterns are less means test time on the ATE machine is very costly. How much time you will hire the ATE machine, that much of cost will be there, but on testing the test cost will reduce. Then reduce the time to market. How fast you can deliver to the product to the market, that also can be reduced by using a DFT. Then, so as I already discussed about controllability and observability, importance of that, developing and applying manufacture testing. This is mainly the purpose for developing, applying manufacture testing. Okay, provide a structural way of testing chip manufacturing defects. Using DFT only we can access each and every node inside an IC. How we will access, that is the thing we want to know now. What we are saying is that each and every node has to be accessed. How we will access it? If it is very deep into the IC లోపల ఎక్కడో ఉంది, IO pins ఎక్కడో ఉన్నాయి. So much of logic is there in between, but still I want to go inside it. So circuit what I have shown is very simple circuit that we can directly set it, but if it is there inside very deeply we can't set it. How we can reach there? That is the DFT will give the solution. Different techniques are there to do it. We will quickly go into that part. Okay, so this is the simple DFT goal, high level definitions. It's not so important. Yeah, go it. Yeah, can go next slide. Yeah, keep it. So these are the different techniques we will be using it. One is the scan design, that is especially used to test the glue logic. What are the register transfer logic that is there inside it, that can be tested it by using the first technique. Other one is boundary scan, that is used to test all the IO pins, pin to pin connections, different ICs, 2 ICs are there. To IC connectivity they will be verifying it. Okay, that boundary scan will be useful, that we will popularly call it as JTAG. So whatever the board you study, maybe you are using so many boards, whatever the board you use it, you will have a JTAG pin. That's a standardized, because they will have different ICs inside it. IC to IC connectivity onto the board, on the board, how will they will verify? This is one of the technique called boundary scan. Other technique is a BIST MBIST, memory BIST, that is popularly called as MBIST. Other one is a logic BIST. Logic BIST is also very similar to this scan design, but it is on real time it will happen. Scan design will not happen on a real time, but logic BIST will happen on a real time, like automobile ICs. On a real time we should be verifying it. Some sensor part is not working, means they should be reporting it. On a space missions, real time is needed. So wherever on medical equipments real time is needed, for that we will use LBIST. Okay, wherever real time applications are there, LBIST will come. Okay, there will be a penalty of DFT. Already we discussed that 30% overhead will be there. Along with the design we have to provide a DFT. So that overhead is a lost, that's the hardware overhead, extra area, extra pins, okay, performance degradation. Because of the DFT, speed also will reduce. Chip speed may reduce slightly. Impact on the speed also will be there. But we have to do it. Ultimately we have to test it each and every transistor. So at expense of that I am doing the DFT. These are the different penalties. Power overhead, power burden, power dissipation also will be more, because extra 30% hardware we are keeping. For that we will have a power tax also will be more, and yield also will be slightly affecting.
And the speed will reduce.
Why?
Speed will reduce.
Speed is reduced because of some DFT hardware, extra DFT hardware what we will add it to set that, to initialize the DFT hardware, we have to sacrifice few cycles, test cycles, to configure the DFT. DFT part, extra hardware will add it for DFT. To configure the DFT hardware, few cycles we have to sacrifice. So that cycles, if it is there, means chip may be faster if that overhead is not there. But if this overhead is not there, if this DFT is not there, means we can't test it. So like that a few more time may take. But the overhead will be there always.
The time cycles and clock cycles.
Clock cycles, that's I mean is the clock cycles only. Okay, SOC design flow. So initially also we have seen the same diagram. But now we see the DFT, I want to show you where the DFT will involve in it. Before synthesis, while RTL design itself, we will use the DFT. We will use DFT, that is DFT aware RTL code. We will write initially DFT code, extra code, to enable the testability. Okay, I am not going deep into it because of lack of time. Okay, so here we will use it. Again, after synthesis also, major thing we will have it after synthesis. Here also we will have it, after synthesis also we will have it, and after routing also we will have it. After silicon, packaging and testing will happen. No? At that time also DFT engineer will be there. So this diagnosing process has to be done by DFT engineer only. So testing engineer we have to support, for testing engineer we have to work as a support for him, because the pattern is designed by me. He is applying it physically, but the pattern is being designed by me. So I have to support them. So any failed chips are there, I have to do the diagnosing, analysis I have to do. So post silicon activity also has to be done. Okay. So like shmoo plots, maybe you heard about any shmoo plot. What they will do it is that for different voltages and different frequencies, how the chip is working, they will make a plot. So that plot we will call it as a shmoo. That will happen generally at this stage of ATE testing. Maybe if possible I will show whenever I do the demo, shmoo plot.
Additional circuitry for DFT.
Traditional?
Additional circuitry, what we have to configure for DFT.
Traditionally what used to be DFT?
Not sir, additional circuitry.
Additional, okay, not traditional, additional. Okay, that only we are going to. Next topic is that one. Okay. So for DFT, what is additional circuitry? That is the topic we are going to next. Okay, that's the scan flip-flop insertion. No, that is the topic we are going to discuss. Yeah, can you go to the next? Yeah, scan design and ATPG. Now, what is the hardware, extra hardware? Next slide. Next. What is extra hardware we will use it? The extra hardware, whatever we use it, that is scan design. That is used to test all the glue logic, all the gates and transistors that are there in design, all this glue logic, that means not an IP or so other than digital part it will not be verifying, only digital part especially that will be mainly it is covered by this scan, basic scan. There are two types of scan. One is the boundary scan, another one is the basic scan. Basic scan we will generally call as an internal scan. Okay. So boundary scan we will call it as an external scan. But more popular is the internal scan. Boundary scan is very little, but most of the effort have to be done on the internal scan. That will be verifying all the logic internally to it. Okay. Next slide. Okay. So internal modification of your design circuit to increase the testability. How you will modify? So to increase the testability, how we will modify the internal circuitry? Okay, that we will see now. Go to the next slide. Okay, here small technique is there. Maybe if it possible, I will link open cheyagalaru. Mouse on my small video that shows the concept of that, then I will discuss it. It's a 1 minute clip. Yeah, there's no need of audio అవసరం ఉండకపోవచ్చు. What it is doing actually? Okay, what actually it is doing? ఏం చేస్తుంది? స్టిక్ లోపల పెడుతుంది అంటే హ్యాండ్స్ తినటం గురించి. whenever it sticks to it, it's taking out and it is eating it. Why it is doing it? Because its hand cannot go inside it. అలాగే మన ప్రోబ్ కూడా ఐసీ లోపలికి వెళ్దు. But how we are testing it? Same concept. What we will do it is that we will serially send a sequence of data into it. Okay. Whenever serially if you send it, all the flops internal chip lo, all the flip flops will be there. So many D flip flops will be there. All D flip flops I will connect as a shift register. I will connect it as a shift register. So shift register may connect chesinappudu, whatever the data you will pump from one of the input, that will goes into all the flops now. all the flops, so that I can set the value onto the flop. Okay, so that is nothing but it is keeping the stick onto the hole. That is nothing, that is the activity. Then what I will do, I will shift out the data, internal node data. It will be captured into the flop again. Next one clock cycle I will give it. It will be captured onto the flop again. So then we will do the shifting out, same. So previously we will done the shifting in. Now we are doing a shift out of the data from the primary output. So at that time what will happen, internal node data will come out from the flops, shifting out. Before shifting, after that the hand should stick into it. No? That is one cycle we will be capturing. So first we will do a shift in, after that we will do capturing. That means the hand should be sticking onto the stick. That is capturing. Then we will be taking out, that is shift out. These three type of activities will be done by a scan design. Actually scan design is nothing but this only. Serially sending the data into all the flops. How I will send all the flops means I have to connect all the flops into shift register fashion. Like that all the data will go into all the flops. Then we will read out, then we will give one pulse to capture the internal node data onto the same flop. Then we will shift out the data. So the data that is being captured by internal nodes, everything will come out from the primary output. So shift in, capture and shift out. These are the three activities we will do it to capture the internal node data values. Okay. Next slide. Yeah, come next. Yeah, you can see here the same concept. Scan in, these are all the D flip-flops. Okay, all D flip-flops are connected as a shift register fashion. So data we will send it to this. Data will capture onto all the flops. Then I will show you the next slide what will happen. Yeah. So any RTL will be like this first diagram. Like combination circuit will be there, all the flops will be there. Now what I will, scan in session means what I will do is that extra, instead of ordinary flop there, I will keep a scan flop. Flop I have changed. The D flip flop I have changed to a scan flop. No other change. All the internal D flip flops I have changed to a scan flop. What is a scan flop? How it looks like? It is like this. Ordinary D flip flop with a small mux. With a mux. I think everybody know about functionality of the mux. SE is the scan enable. Whenever you want to do the scan, we will make it as a 1. Then what will happen? From SI data will come inside. How it is connected here? SI is connected to here and this output is connected to here. Then it will become as a shift register or not. Whenever SE is equal to 1, that circuit will become as a shift register. So I can shift the data inside. Okay. So whenever SE is equal to 0, what will happen? It will take the data from the internal nodes. From the combination circuits, it will take the value. So one example, we have seen an example. That example may be there inside this COM circuit. That output of the COM circuit will be going to the flop. That COM circuit output will go into the flop. Again the data has to come out. How it will come out? While doing shifting, it will set the combination circuit inputs. One example we have seen previously, inputs and outputs. Small circuit we have seen. Inputs will be set whenever you do a shift in. Output will be collected whenever you do the shift out. In between, one clock cycle we will provide it in the functional path. That means at that time we will make it as SE is equal to 0. From COM path it will take. One cycle it will take the COM path. Whenever SE is equal to 0, it will take that value, COM value, and it will load into the flop. So then that data can come out. Okay. Maybe next slide when we have more explanation. Yeah, maybe you can see here. shift in, capture, shift out. 3 activities will be there. Shift in means at the time all the COM circuit inputs will be set. Okay. All the COM circuits inputs will be set. During capture, the COM circuit output will be captured. During shift out, the captured output value will be given to the primary output like a shift register fashion again. Only during capture, at what time capture time, you should come from COM circuit. COM circuit means what value we should have it for scan enable? We should have a 0. Only it takes from a COM circuit. Original circuit is from COM circuit. For the sake of testing, what we have done it is that ordinary D flip-flop we have converted into a scan flop. By doing so, each and every COM circuit you can read the value. Are you getting what the technique here? If you understand these 3 steps, how it is happening, that is nothing but a scan. Do you understand the basic of it here? Maybe step-by-step procedure also there. Maybe we can go to next slide. Yeah, this is the summary of all the step 1 to step 7. Okay. So all each and step, every step I have made it one diagrams for each step. Yeah. So this step, what will happen is that there is no, these things are the flops. Okay. This is the scan input and this is the scan output. These are the flops. Okay. So at that time there is no data inside it. Next slide. Then step 1 will start. At the step 1 what I will do is equal to 1 I will keep it, scan enable. So scan enable is 1 means it is connected as a shift register. So whenever it is connected as a shift register, initially there is no data. So that is X. All the data whatever I want to keep it, I will keep it from scan in. One extra pin I have to give it to IC. From that I will be sending the data. Then this value will be loaded. You can see that 0, 1, 1 has been loaded. Next one, next slide. Then the remaining all the flops are being loaded. Okay. So the data has been loaded now. That means shifting has happened. Next what has to be done? Combination circuit output I have to collect it. That COM output to collect it, I have to make a scan enable is equal to 0. If I make scan enable is equal to 0, I will be collecting the COM data onto the flop again. Next. Okay. I have collected the data. Okay. Step 3 and step 4. Okay. Whenever I collect the data, so ordinary primary input data also has to be set. And also this last COM data also has to be read out. That also will happen here. Next. Next one, shift out. This is the activity of a shift out. Okay. Actually it is loading into the flop. Actually it is loading into the flop. Next slide. Yeah, now it is shifting out. Now scan enable become as a 1. It is shifting out. Like that I can load any value onto the COM circuit internal to it. And I can read the value from the flops by making behaving flop as a shift register. It is a big shift register. Okay? Yeah.
Why this process? Actually,
Because we can't touch, internal COM circuit is there. You can't touch the inputs. How we can reach there? Through flops.
actually, doctor, we are giving some scanning shifting process, we are sending some data. And to that again we are from the combination circuit, we are going to get some data. What is happening, this data
Okay.
overwriting?
What will happen with the shifting data? The shifting data will set the COM circuit input values.
The next COM circuit input value.
Yes. Okay. That COM circuit output value will be collected by shift out. First shift in whatever you do, you will set the values of COM. Shift out will collect the values from COM. Shifts out the values from the COM circuit. But middle one cycle will be there. That will capture the COM circuit output onto the flop. Then it will be shifted out. That because the same principle of Chimpanzee keeping a stick here and attaching it. Attaching is nothing but capture and again bringing it out, shift out. Maybe it is very close to that behavior of the chimpanzee activity. So I tried to keep that video.
So all the primary inputs are inputs acting on the first combinational logic.
Yes, first combinational logic.
Outputs are the output of the last.
But all combination, last combinational output directly it can read it on the primary output. There is no shifting is needed. Okay, these are the different steps involved in it. Yeah, this is once it is shifted out, new data will come into it again. All the data is shifted out now, then new data will come onto the loaded into the next flop. One cycle of shift in, capture and shift out is one pattern. Is one pattern we will call. Okay, so there are 4 steps will be there in scan synthesis. That means to implement the scan. First what has to be done is that all the flops. Another one is that not all the D flip-flops we will convert into scan flop. Few flops we will not touch it. Suppose some cryptography is there. Cryptographic unit, they don't want to touch, anybody should not touch it. DFT also cannot touch it. So they will skip that block. Okay, those flops they have to skip it. That is the reason only few are colored ones, few are left out. Some special cases flops will be there. That nobody, the designer don't want to insert a DFT scan onto it. He don't want to test it also. If requirement is there like that, we have to leave it. They will give us the requirement, which flops we should not touch it. So that flops we will not convert into shift register. We will leave it. But we are having another approach to cover that. But that technique I don't want to discuss now. It's another technique to cover those things. We should not leave it now. We want 99% accuracy. So then replace all the configured flops into scan flops, then reorder it so that the wire connection will be less. If you reorder the connectivity, shift register length will be less. So reorder the thing and then stitch it as a shift register. So these 4 activities will be done. Yeah. As the implementation perspective on a tool, these are the basic steps after design, RTL code. Whenever a gate level netlist is there, it will be like this. After scan is inserted, all the flops will be converted into scan flops. I want to show you one demo to show that at the gate level how it is there before, how it is there after that. Okay, this is one thing I want to show you. So after scan is inserted, we will perform ATPG patterns. We have to generate the patterns. Then patterns are generated and those patterns will be the output to this scan process. Okay, so that is about the scan design. Yeah, that ATPG. Coming to ATPG. So what I am saying, one step back, next step. What I am saying is the ATPG. Now, how we will generate the patterns? Next question is that already, next slide. Already we have discussed how we will be doing it. That will happen in 3 stages. Fault activation, path sensitization and line justification. First one is fault activation. Fault activation means, next slide. Okay, fault activation means what fault I want to test it. I want to test a stuck at 1 fault on this. That has to be activated first. So I want to make a stuck at 1 on the output of the AND gate. That means node E. What value I have to set it now? Opposite value. 0. How will I set a 0 on this? Can I make a 0, 0 here? AND gate? I can make it. That means I can control that E. Can I observe that value onto the output G? Can I observe it? If I give 1, 1, what is the value of this OR gate? It will be, not of that, it will be 0. So 0. So that value can be observed on G. Suppose I want to test the value on C. Stuck at 1 I want to do it. Same stuck at 1. That means what is the value I have to keep on C? 0. So direct input DB, so I can directly keep a 0. Controlling is not an effect, not a problem effect at all. But observing means I have to see it on the output. Observing, you have to see on output. So this has to be propagated. 0 has to be propagated means complement of that will be 1. So that 1 has to come on the G. Okay. So how will be 1 will get it? If it's a 0 input, AND gate always will become a 0. So then there is a way, yeah, one of the OR gate is 0 means other input it can propagate whatever may the value. Yeah, we can control it and we can observe it. Okay. So what is the ATPG is that for each and every node, it will tries to control it first. Controlling is nothing but, step one slide. Okay. Controlling is nothing but path activation, path sensitization. Okay. Observing the value onto the output step is called a line justification. Fault activation means what we want to test it. Stuck at 0 or stuck at 1, which node? That has to be decided first. So these 3 steps is nothing but ATPG. These 3 steps is nothing but a ATPG. There are so many complications are there in it, but I don't want to go into it. To make it simple, I made it 3 steps. Okay, that's nothing but maybe popularly known algorithm for that is a D algorithm. D algorithm. Maybe MTech VLSI people, they know about it. That will do these 3 steps only. But mathematically there is equations will be there for that. Yeah. Next. The fault activation. Next. For path sensitization. That means path sensitization is the output it is coming. Yeah. Then line justification. Yeah. This is one example of that already we discussed. Yeah. Like that, for all the circuits we have to do it. For all the COM circuits we have to do all these steps by ATPG. If the chip is very large like this, maybe this is an example of Core i7 processor. So many circuits. For ATPG, is it so easy to do it? It's hard. That is the task that a DFT engineer has to do to cover all the things, because I can't do this scan design, the technique I can't apply for a memory. I can't apply for a memory. I can't apply for ADCs. I can't apply for oscillators. I can't apply for analog circuits. This is only the set that is applied for the glue logic. One technique. Like the different techniques are there for each and every component to cover it. Okay, an example I am showing one of this approach. Okay, finally conclusion of that, what is the ATPG? The goal of ATPG is to create a set of patterns that achieves the give to a good test coverage. What do you mean by a test coverage? Suppose 5000 transistors, what we are discussing from starting. If I cover all the 5000 transistors and all the nodes of the transistor, my coverage is 100%. But practically the value you will get it is 99%. First, racket faults. For transition faults, we will get it 95 only. That is our general goal, so we will achieve it. We can't get 100% testing. At least 1% will be left out. So the product, whatever you are getting it, 1% of that is being not tested. There is no feasibility to test. Okay, that still that 1% is we are losing it. That we have to get up to the max value. Generally the goals for us will be like we have to get 99% coverage like that. So suppose some coverage is not there, means we have to go for other approach. The different techniques are there for us. For a simple thing I am telling it, but there are so many other techniques like this. But it will sits around this technique only. Slight variation to this technique only. Okay. Okay, there are 2 methods for pattern generation. One is random and another one is deterministic. Random one means it will randomly give some pattern. It will test how many nodes are being tested out. So once randomized in nature is not giving any output, then they will go for a deterministic one. Deterministic one means algorithm point of view, like D algorithm they will apply. That is a deterministic approach. Okay, there are 2 different approaches are there. Next. Procedure of number of random patterns identified only by this. Okay, this is not so important. You can go up. Next one. Yeah, finally the coverage, how many nodes are covered, we will get a report like this. So here in this case, coverage, where it is there, you can see here, test coverage. is 99.101. And all the nodes are being tested. Okay. So that means almost all the nodes are casted, and they will have a categorization of this for detected false, possible detected, detectable, ATPG, and these are the different false categories will be there. So, okay, so scan design is what's the time now? (4:15). Okay. So can you spare me another 5 to 10 minutes? I will show one demonstration and then I will close the same scan approach. I may not be discussing about MBIST and boundary scan. Actually, I plan to do it, but times versus will go off. Demonstration, there is no possibility. If you can give me, you tell me, otherwise we will close it. What's your opinion? What's your plan? It's up to you. Real time, whatever the design is there, just I will run it and show you, otherwise we will close it now. Cheppandamma.
Okay, sir.
Okay, 5 minutes, okay. HDMI ఉందా పోర్టు HDMI కదా HDMI పోర్ట్ అంటే జస్ట్ ప్రొజెక్టర్ కనెక్టెడ్ HDMI పోర్ట్ ఉందమ్మా
ఆడియో ఉంటుంది సార్
ఆడియో అవసరం కింద పెట్టుకుంటే బెటర్ ఈజీ సైజ్ వస్తుందా is not coming. Sorry, mobile data I am not getting it. Oh, mobile data is gone. Wi-Fi. Oh, it will like మళ్ళీ కాన్ఫిగర్ చేయడానికి టైం పడుతుంది వైఫై అంటే మొబైల్ డేటా ఆల్రెడీ సెట్ చేసాము. వద్దు అవ్వకూడదు వద్దు వద్దు అన్నదైతే వద్దు ఐపీ చేంజ్ చేస్తుంది వద్దు అయితే సబ్ సెక్యూర్ ఓకే లెట్ us లీవ్ ఇట్ ఓకే నాట్ వేస్ట్ ఆఫ్ టైం వద్దులేండి అయితే సో ఫర్ సెక్యూరిటీ రీజన్ ఐ కాంట్ మేక్ ఇట్ ఐపీ చేంజ్ నో యా ఓకే That is one technique. Okay, we will close the session then.